Welcome to Biology Made Easy. In today's lesson, we are discussing how to use the respirometer to measure the rate of respiration with time, the rate of respiration under different temperature conditions. We'll use the respirometer to measure the respiratory quotient. We'll also look at the calorimeter. Using the respirometer to measure oxygen uptake during respiration, we have the respirometer set up. We discussed it in our last lesson, check. Now, before the experiment, you see this syringe, its purpose is to push in air into the system. When it does that, it will set the manometer fluid the same at the beginning of the experiment. Then the screw clip is also closed at the beginning of the experiment. Now, if the organism here respires, the organism will use oxygen up, produce carbon dioxide. That's the wool house, you produce carbon dioxide. The carbon dioxide is absorbed by the soda lime. So the oxygen that is absorbed will reduce the pressure in here. And so if the pressure here reduces to be less than the pressure here, and so we'll have a difference in the manometer level, showing the amount of oxygen that has been absorbed. So change in the fluid level corresponds to the amount of oxygen absorbed, and that's change so if the change is monitored with time, say every 1 minute, amount of oxygen consumed, which is equivalent to the change of levels here, time every minute is plotted, we can have a graph of respiration against time. Now, notice that in the experiment, these containers are in a water bath to keep the temperatures the same and also to prevent fluctuations due to external environment changes. But the same setup can be used to measure amount of oxygen absorbed at different temperatures if the temperatures in the water bath are changed and the temperatures are noted. Then we can plot a graph of oxygen consumption against temperature. Now, remember that at the beginning of any new temperature, the syringe is used to set the manometer fluid at a base in each of the arms. Now, the manometer is also used to calculate the respiratory quotient. The respiratory quotient is a ratio of carbon dioxide produced against oxygen consumed per unit time by an organism. So if we have aerobic respiration, this is glucose, this plus oxygen producing carbon dioxide and water, the respiratory quotient will be volume of carbon dioxide against volume of oxygen, or moles or molecules of carbon dioxide as against moles or molecules of oxygen. And you see that in aerobic respiration using glucose, we have carbon dioxide is 6, oxygen is 6. So the respiratory quotient, glucose, is 1. The respiratory quotient tells us about the substrate the organism is using, because glucose will give 1, triglycerides, fatty, will give us 0.7, protein will give us 0.9. The respirometer can be used to calculate the respiratory quotient, and this is how it is done. So we have our respirometer. At the beginning of each experiment, we need to make sure that the manometer fluid levels are the same in the two arms, and we do that by using the syringe to push air in to set the levels the same. We need to make sure that the temperatures are the same. We also need to make sure that the screw clip is closed at the beginning of the experiment, and also remember to open the screw clip at the end of the experiment. So the first thing we want to do is to measure the volume of oxygen consumed, and that we do by providing soda lime to absorb the carbon dioxide. So we have soda lime here, it absorbs carbon dioxide. The wood lice consumes oxygen, produces carbon dioxide. The soda lime absorbs the the carbon dioxide. So the oxygen consumed for respiration will reduce the pressure here. So if the pressure here reduces, then the volume here will move up and the pressure here down. We have soda lime here. Wood lice consumes oxygen for respiration, produces carbon dioxide. Soda lime absorbs the carbon dioxide, and so the pressure here, because the oxygen is also absorbed for respiration, the pressure of air reduces, and so the manometer level will rise up here as this pressure presses it down. So X will give us the volume of air consumed, and that is given as X centimeter cube per minute. If you have the same setup and no soda lime here to absorb the carbon dioxide that is produced, it means that the oxygen that is consumed by respiration reduces the pressure here. Carbon dioxide produced, there's no soda lime to absorb it, and so if there's carbon dioxide here, no oxygen here, and we have the same level as X, then the X gives us the amount of carbon dioxide, which is equal to the amount of oxygen consumed, because there's no level change here, the same here. And so the X, we have found it as the amount of carbon dioxide produced, and so the RQ will be X over X, which is 1. Now, a substrate which produces this, we can say is glucose. Now, if we have a substrate that the organism is using for respiration that produces more carbon dioxide, then it means the more carbon dioxide will increase the pressure here and reduce the level of the fluid in the manometer here by Y, reduces more than this state. So it reduces it by Y. And so in this state, the volume of carbon dioxide is X plus Y, and the volume of oxygen, which we have found as X, is still X. So the RQ will be this, when the substrate produces more carbon dioxide than in this situation. Then if you have another situation where the substrate that is being respired produces less carbon dioxide than X, then less carbon dioxide, it means the pressure here is low, so the pressure here will push it down, and so the less carbon dioxide that is produced raises the pressure here to Z, increases. The less carbon dioxide that is produced here shows up as Z here, low carbon dioxide. And so here the amount of carbon dioxide is X minus Z. And as we know, the amount of oxygen consumed is always the same here. So this is how we will find the RQ in this situation too, when the substrate being respired produces less carbon dioxide. So we have a simple respirometer here. This is a boiling tube. We have soda lime here to absorb carbon dioxide. You have cotton wool here. You have blowfly larvae here, or any organism. Then this boiling tube is connected to a capillary tube. There's a scale attached to the capillary tube, and there's a drop of water that is colored trapped into the capillary tube. Now the boiling tube is immersed in a water bath to give a good temperature. The setup can be left for about 15 minutes. The organism here will absorb oxygen in here to respire, produce carbon dioxide. The carbon dioxide will be absorbed by the soda lime. The pressure in here is reduced, and so atmospheric pressure is greater, so it presses on the drop of water, and the drop of water will move. So the drop of water moves equivalent to the amount of oxygen removed by the blowfly for respiration. So the amount of oxygen that is removed is equivalent to the distance this bubble travels with time. So the distance the bubble travels with time can be measured, and the distance gives an indication of respiratory rate. So the volume of air consumed can be found out using this equation. This is pi r squared. R is the radius of the bore of the capillary tube, and so the volume of air is written against time, the volume of air every 1 minute. Then the graph can be plotted of respiration against time, or amount of oxygen consumed against time. Now, the same setup can be used instead of the blowfly, any other organism, or germinating seeds can be used. And the same thing found about the respiratory rate of germinating seeds. Now, if the boiling tube is immersed in different temperatures, that is when you are using the germinating seeds, the boiling tube can be put in different temperatures, and so the amount of oxygen used against temperature can be plotted, and that can give an indication of the effect of temperature on respiration using this simple respirometer. Finally, for today, a simple calorimeter can be used to measure the energy values of respiratory substrates. This is like a simple calorimeter. Here you have water, back in here you have your thermometer, measures the temperatures, and here is a crucible with the substrate inside, oxygen inlet into the system here, and light is set onto the substrates, and the measures of temperature will give an indication of the energy value of the substrate, and so different substrates produces different energy. This is where we end for today. The lessons have been useful. Give us your like and kindly subscribe. Thank you very much. Bye bye.